Welcome back to the Deep Dive, powered by Neural Intel. Today, we're plunging into a truly fascinating problem at the cutting edge of AI development. Imagine for a moment you're training an AI model so vast, so incredibly complex, that it just can't possibly fit on a single machine.
Yeah, we're talking models with, trillions of parameters.
Exactly, trillions.
Yeah.
And they need to be spread across dozens, hundreds, maybe even thousands of powerful computers. Now, here's the kicker. These aren't your pristine, perfectly synchronized servers you'd find in, like, a high-performance computing cluster.
Right. Think more. Distributed.
Scattered across the globe, connected by the public internet, some perhaps even on those cheaper, less reliable spot instances that can just vanish. How on earth do you keep that massive model perfectly in sync, training robustly, and completely free from constant crashes, even when machines are dropping in and out like dominoes?
That is the million-dollar question, isn't it? Or maybe trillion-dollar, given the models.
Maybe. That, my friends, is the truly wild problem we're unraveling today. We're embarking on a deep dive into something called the Prime Collective Communications Library, or PCCL.
PCCL, yeah.
This isn't just another piece of software. It's a novel and, frankly, incredibly ambitious solution, tackling what many thought was an almost insurmountable challenge:
Which is?
enabling large-scale distributed machine learning workloads to run reliably and efficiently over the public internet.
Okay. And what's truly revolutionary about PCCL, I think, is that it isn't just about making communication faster. That's important, sure. But it's fundamentally about making it resilient and reliable in these really challenging environments.
Resilient. Okay.
Its core mission is to enable dynamic peer joining so machines can come and go, and robust fault recovery for these geographically dispersed, often unreliable ML training setups. The goal is audacious. Keep your models training, and crucially, keep them in perfect bit parity.
Bit parity, meaning identical down to the last bit.
Exactly identical. Even when the underlying network connections or compute resources are in constant flux, constantly changing, sometimes even failing completely.
Wow. Okay, so whether you're an engineer trying to leverage those cost-effective spot instances to, slash your training budget.
Which is a huge deal economically.
Right. Or maybe you're a researcher looking to build a multi-cloud or hybrid cloud setup for unprecedented flexibility. Or maybe you're just someone who wants to understand how to make large-scale distributed ML truly resilient and robust in the real world. This deep dive is going to be incredibly insightful for you. And as always here, we'll be focusing purely on the technical innovations that make PCCL tick and their profound implications for the future of AI. Okay, let's start by setting the stage a bit. The sheer scale of modern machine learning models has just exploded. It's almost beyond recognition from just a few years ago.
Absolutely. We're not talking millions of parameters anymore. Some models are now boasting trillions. Trillions.
It's hard to even wrap your head around. And this monumental scale absolutely necessitates distributed training. It just pushes the boundaries of what any single machine, no matter how powerful, can possibly handle.
You just can't fit it all in one place.
No way. So we're talking about orchestrating these vast clusters of GPUs or specialized accelerators, all working together, all needing to contribute to the same single model.
And this isn't just about having a lot of machines sitting there. These distributed workloads are, by their very nature, intensely communication intensive.
Right, they have to talk to each other constantly.
Constantly. Think about it. Every single parameter update, every gradient calculation, all that critical information needs to be meticulously synchronized across potentially hundreds or thousands of these worker nodes. If these nodes aren't talking to each other efficiently and reliably, the whole system either grinds to a halt,
Which is bad enough.
or far worse, it starts producing inconsistent, non-reproducible results. And that's where the foundation of trust in your model just starts to erode. You can't rely on it.
Exactly. And for years, we've had these powerhouse tools designed for high-performance computing, like MPI, the message passing interface. You hear about that a lot in science.
A classic.
And NVIDIA's NCCL, the NVIDIA Collective Communications Library. These are absolute staples in those tightly coupled, often purpose-built, high-performance computing clusters.
The supercomputer kind of environment.
Yeah, the kind you find in supercomputers or dedicated, pristine data centers. They're incredibly optimized, built for raw speed within those specific controlled environments.
And they are phenomenal within that domain, no question. The problem is these traditional libraries operate on a set of assumptions that, well, they rarely hold true in the distributed ML world we're increasingly moving towards.
What kind of assumptions?
Well, they assume a fixed membership, meaning the number and identity of nodes doesn't change once a job starts. Everyone who starts is everyone who finishes.
Okay, static group.
Exactly. They assume predictable node connectivity, often with incredibly fast, low latency interconnects like InfiniBand and uniform performance characteristics across all machines. Basically, they're designed for a controlled, pristine environment, almost like a digital operating room.
Clean room conditions.
Pretty much. And the fundamental issue is that these assumptions just crumble when you move to the massive scale of modern ML, or, critically, when you try to extend beyond those dedicated HPC clusters onto more dynamic public networks like the internet. And what truly cripples these traditional libraries in dynamic settings is their complete lack of graceful handling for what we call peer churn.
Peer churn. Love that term.
Yeah, it's a descriptive, right? It's when nodes fail or new ones join, or maybe they just disconnect unexpectedly. Imagine a node suddenly going offline right in the middle of a complex gradient aggregation.
Oh, boy.
Or a new server being brought online mid-training. MPI or NCCL simply weren't built to recover from that gracefully. An event like that would typically lead to a complete job crash.
Everything stops.
Everything stops. And you face a frustrating restart, forcing you to begin again from the last checkpoint, potentially losing hours, maybe even days, of valuable compute time and progress.
So if you're an engineer or data scientist trying to train across public clouds, maybe trying to save money with those volatile spot instances,
Which is a huge driver for this.
or dealing with unreliable networks that span continents, what does this all mean for you in practice?
Pain. Mostly pain.
Huh. Yeah, it means constant frustration. It means endless job restarts. It means a complete lack of the resilience you need for practical, large-scale, and especially cost-effective deployment. You simply cannot rely on a system that falls over every time a single component hiccups, especially when those components, like spot instances or WAN connections, are inherently designed to be somewhat unpredictable.
It's like trying to build a skyscraper, as you said, with a foundation that cracks every time a strong wind blows. It's just not viable. And this is precisely the critical void PCCL steps in to fill. It's built from the ground up with public networks in mind, acknowledging that in these environments, peers are often in motion, and instability isn't an exception, but often the norm.
It accepts the chaos.
It accepts the chaos, exactly. Its core design principle fundamentally accepts that dynamic environments are not just a feature of the future, but a reality of the present for distributed ML. Its key innovations are really twofold: dynamic peer membership and robust fault tolerance mechanisms.
Okay.
These allow collective operations, like that crucial step of aggregating gradients, to continue unimpeded even when peers are coming and going or experiencing intermittent failures. And here's a crucial technical detail, really fundamental to its consistency model. PCCL leverages the deterministic nature of most modern optimizers, like AtomW.
Deterministic meaning.
Meaning if you give them the exact same input, they produce the exact same output down to the last bit. So if all peers receive identical updates and PCCL ensures they do, then bit identical state progression is guaranteed. Even when these operations are performed on different GPUs across different machines, maybe even different GPU architectures.
Wow.
This is not just a nicety, it's fundamental. It ensures that every single parameter in your massive model on every single machine is exactly the same. It eliminates those tiny accumulated floating point discrepancies that can otherwise derail a massive training run and make results completely non-reproducible.
That concept of bit identical state progression is huge. Can you give us a sense of the practical pain point before this? Like how much time was lost dealing with these tiny differences?
Oh, immense amounts of time. Before something like PCCL providing this low-level guarantee, ensuring bit identical state across widely distributed, potentially heterogeneous systems was frankly a nightmare.
What do people do?
Engineers would often resort to really cumbersome application-level checkpoints and complex multi-stage synchronization protocols just to verify consistency. Think extra communication overhead, just checking if everyone agrees.
More communication, more latency.
Exactly. Or even worse, it meant painstakingly debugging training runs that diverged for seemingly no reason, maybe after days of running, only to discover some subtle floating point difference on one machine, maybe due to a slightly different library version or even hardware that propagated and eventually corrupted the entire model state.
So a multi-day run could just fail at the very end.
Absolutely. Imagine that happening. The financial cost, the time cost. It was immense. PCCL's approach, by ensuring this deterministic update propagation, makes that global truth inherent in the process itself. It dramatically simplifies things and makes large-scale training genuinely reliable in a way it wasn't before.
That precision in determinism really sets a new standard. It's a massive shift from previous approaches that couldn't reliably guarantee that consistency without adding all this extra communication overhead just to maintain a global truth.
PCCL aims for that truth to be inherent right from the start.
Okay, so that guarantee of bit-identical state progression sounds incredibly powerful.
Hmm.
But let's talk about how that's actually achieved at an architectural level. You mentioned PCCL uses a master-client model, which is different from traditional setups where maybe all processes start together in a synchronized Big Bang.
Right, it's a different philosophy.
This immediately makes me wonder about that master. How does it operate? And isn't it potentially a single point of failure? That's usually the first worry with masters.
That's a very perceptive question, and it gets right to the heart of PCCL's design choices. So in PCCL, the individual training processes, the things actually doing the model computation, are the clients or peers.
Okay.
Each client process starts up, creates its own PCCL communicator instance, and then connects to a central lightweight master process. These clients then go through a state transition. They start as registered. You can think of it like being on a waiting list or knocking on the door.
Waiting to get
Exactly. And they only transition to an accepted or active state through a quite sophisticated voting mechanism among the peers that are already active in the group.
So the existing members have a say.
Yes, it's a consensus process. Now, the master node itself, it's purely supervisory and coordinative. It doesn't actually participate in the heavy lifting of data transfer for the collective operations like all reduce. That's crucial for performance. It doesn't become a data bottleneck.
So it's just orchestrating.
Precisely. Its role is to maintain a consistent, up-to-date view of all the accepted peers, to track and optimize the ring topology used for things like all reduce, and most critically, to coordinate all state transitions like peers joining, leaving, or operations starting and finishing through a series of micro-consensus steps.
Micro-consensus.
Yes, small, quick consensus steps among the peers orchestrated by the master. This rigorous, centralized coordination is absolutely central to PCCL's robustness and its ability to actually manage dynamic membership effectively.
Okay, but back to that single point of failure concern. A centralized master in a system explicitly designed for resilience. It still sounds risky.
Yeah.
How does PCCL square that circle?
It's a very valid concern, and it's one the paper directly addresses. They even call the master an authoritarian node, which is quite a term.
Authoritarian.
But while it does introduce a central orchestrator, the paper argues, and I think convincingly, that this master node is absolutely key to making fault tolerance tractable in these highly dynamic environments. They mention that previous internal attempts at building something similar failed precisely because the API was too permissive. Peers could join and leave essentially anytime they wanted, leading to an almost uncountable number of possible system states and a combinatorial explosion of potential error paths. It became impossible to reason about, let alone guarantee, robust fault tolerance.
Too much freedom led to chaos.
Exactly. By strictly limiting the legal state transitions and coordinating them through the master, PCCL drastically simplifies the problem space. It makes the potential error paths enumerable, which means they can be systematically tested and handled. It turns what was an intractable mess into a manageable engineering problem. Think of it like a highly skilled air traffic controller. Yes, the control tower is central, but its job is to guide planes safely, manage landings and takeoffs, not to fly the planes themselves. The alternative, where every plane just flies wherever it wants,
is chaos and collisions.
Right. The master streamlines the decision-making for membership changes and state synchronization, ensuring everyone stays on the same page.
That makes a lot of sense. Sometimes you need that central authority to bring order. So walk me through it. A new machine wants to join this carefully orchestrated party. How does that process work, and what specific details does this master need to keep track of to maintain such tight control?
Okay, so when a new peer wants to join, it connects to the master and enters that initial registered phase. It's essentially raised its hand and said, I'm here, I want in.
Knocking on the door.
Exactly. The existing, already accepted peers then periodically check with the master if there are any registered peers waiting. If there are, they conduct a vote, another micro-consensus step, on whether to admit this newcomer into their active group. If they collectively agree, yes, let this one in, the master then instructs all the accepted peers, including the newcomer, to establish the necessary direct peer-to-peer, P2P network connections with each other.
Ah, so they talk directly after being admitted.
Yes, for the actual data transfer in collectives, and this is a critical point. This controlled admission process allows peer churn, allows new machines to join, without forcing a full restart of the entire training job. That's a massive efficiency gain compared to traditional systems where adding a node meant stopping everything.
Huge. Okay, so what's the master tracking behind the scenes?
The master node tracks several critical pieces of information to maintain this order. First, obviously, it keeps tabs on the clients and their status, clearly differentiating between registered peers waiting outside and accepted peers who are actively part of the collective group.
Got it. Registered versus accepted.
Second, and this is where things get really clever, especially for optimizing performance over the wide area network, WAN, it's responsible for the ring topology and bandwidth metrics.
Ring topology for the all reduce.
Exactly. Based on direct peer-to-peer bandwidth tests that the peers conduct periodically and report back, the master attempts to optimize the logical ring order used for collective operations, particularly the all-reduce. Why? Because the order matters a lot for performance, especially with varying latencies between nodes.
So it tries to find the fastest path.
Precisely. It solves what's known as an asymmetric traveling salesman problem, or ATSP. Finding the optimal ring that minimizes total communication time, considering potentially different bandwidths and latencies in each direction between pairs of nodes. For this, they actually developed a custom heuristic solver and an exact ATSP solver library called libsp.
Wow, they built their own TSP solver.
Yeah, which shows the level of detail they went into for optimization. And this optimization isn't just a one-off thing at the start. It can happen as a quick pass, find a decent solution quickly within a timeout, or as a more involved moonshot background computation, trying to find an even better ring order as network conditions perhaps change over time. Once a new or improved ring order is determined, the master instructs all the peers to reconfigure their peer-to-peer connections to match this new optimized topology.
So if I'm understanding this right, the master node is literally redrawing the map of the most efficient communication pathways in real time, or near real time.
That's a great way to put it.
That sounds like it would naturally exploit low-latency local paths, maybe nodes in the same data center, and actively minimize those expensive high-latency hops across the public internet. This is a huge performance gain, isn't it? Not just a stability feature.
Absolutely. The paper really emphasizes this as a key benefit, particularly for performance over WANs. It's intelligent routing built right into the communication layer. Then there's the shared state. The master plays a crucial role in ensuring that every single peer maintains an identical shared state. This isn't just the model parameters, it also includes the critical optimizer states, momentum buffers, variance trackers, all that stuff.
Everything needed to resume identically.
Exactly. If a peer is identified as having an out-of-date revision or worse, mismatched content, maybe it dropped out for a while and rejoined the master instructs it to request the correct up-to-date data directly from another peer that is up-to-date. This ensures all participants converge back to a bit-identical set of parameters and optimizer state, which is absolutely essential for that deterministic training progression we talked about. This process leverages a simple, non-cryptographic, purpose-built, and highly parallelizable hashing function they call simple hash.
Simple hash.
Yeah, it's designed to be fast and crucially deterministic across platforms. They internally verified it on GPUs for determinism across different generations, from older GTX 980 Ti's all the way to cutting-edge B200s, and also implemented a version on the CPU using OpenMP for broader compatibility if needed.
So they're hashing the state to check for consistency.
Precisely. A quick, deterministic check. And finally, the master coordinates the collective operations themselves. It acts as a gatekeeper, strictly preventing conflicts between various major operations. You can't be accepting new peers while also trying to run an all-reduce and synchronizing state all at the same time. That would be chaos.
One major thing at a time.
One major state-changing operation per peer group at any given moment. While the master coordinates these operations, gives the go signal, confirms completion. It's critical to remember it's not actually involved in the data transfer or the shared state retransmissions itself. It doesn't touch the actual model data.
Stays out of the data path.
Right. Its role is solely to ensure consensus among all peers that an operation has completed successfully and to propagate any I/O failures quickly to prevent the system from stalling or diverging.
That master-controlled coordination sounds incredibly precise. But here's where, the rubber really meets the road. How does PCCL handle a peer dropping mid-operation, right in the middle of an all-reduce, say? How does it avoid everything devolving into chaos? That seems like the ultimate stress test for resilience in a distributed system.
It absolutely is, and it's a core design challenge they've tackled head-on with a combination of a sophisticated state machine and those extremely strict operational rules we just discussed. Each major operation, like an all-reduce, proceeds through a series of very well-defined phases. The paper mentions states like connection phase, connection state, and collective communication state, the last one being tracked per specific operation using a unique tag. Now, every single transition between these states requires what they call micro-consensus.
That term again.
Yes. It means unanimous agreement among all the involved peers, orchestrated via the master, before the system can move to the next phase of the operation. This immediate unanimous agreement mechanism is what enables rapid detection and handling of any inconsistencies or partial failures. If one peer fails to agree or respond within a timeout,
It's caught immediately.
instantly, the system knows something is wrong rather than waiting indefinitely or proceeding with incomplete information. And reinforcing this is that strict rule we mentioned. Only one major operation, be it accepting new peers, synchronizing shared state, or running a collective like All-Reduce, can be active per peer group at any given moment.
No multitasking on the big stuff.
Exactly. This ensures correctness and predictability, especially when membership might be changing dynamically. It prevents complex race conditions or conflicting state changes that could undermine that all-important consistency and bit parity guarantee.
That one operation at a time rule seems quite strict, maybe even a bit limiting, but I guess it makes sense if you absolutely have to guarantee bit parity in such a dynamic, potentially messy environment.
It's a trade-off, certainly, but it's the trade-off they made to achieve that level of robustness.
So what happens practically if a peer just vanishes? Mid-collective, poof, gone. Does the whole system just grind to a halt then?
No, absolutely not. That would defeat the purpose. If a peer disappears mid-collective, PCCL doesn't just crash the whole job. Instead, it detects the failure. Because that peer stops responding to micro-consensus checks or its connection breaks, cancels the current attempt of that collective operation, aborts it cleanly, marks the peer as gone in the master's view. And crucially, it then allows the application developer, the person writing the training script, to simply retry that collective operation. But this time, the retry happens without the failed peer included in the group.
So the group shrinks and the operation tries again.
Precisely. This is incredibly important because it prevents a single point of failure, one flaky machine, from bringing down the entire multi-million-dollar training run. Furthermore, the application developers can specify a user-defined threshold. Let's say, I need at least 80% of my initial peers to keep training effectively. If the number of active peers drops below that threshold due to failures,
Training pauses.
training can automatically pause, yes. This gives time for maybe new spot instances to spin up and join, or for manual intervention if needed, rather than continuing inefficiently with too few workers.
And what about the other side, accepting new peers? How is that robust enough to prevent, say, a stream of flaky new connections from constantly destabilizing the core group? It sounds like a delicate balancing act.
It is indeed, and the process is designed to be cautious. New peers remain in that registered state we mentioned earlier, waiting outside the door until the existing trusted peers explicitly vote them in via that consensus step.
The members get to decide.
Right. Now, if any part of that connection process fails, maybe the master has trouble coordinating the new peer's inclusion, or maybe the direct peer-to-peer links can't be established reliably with the newcomer. The peers can either retry the connection attempt a few times, or if the issue persists, they can simply vote to reject the newcomer entirely.
Sorry, you're too flaky. Try again later.
Essentially, yes. This preserves the stability and consistency of the existing group. They don't let unreliable newcomers disrupt the ongoing work. This controlled, master-coordinated admission process is precisely what makes fault tolerance tractable. The paper explicitly states that previous, more permissive designs where peers could just join and leave whenever they wanted created an unmanageable number of system states and edge cases and proved impossible to make truly fault-tolerant. PCCL's strictness here, its authoritarian master, is actually its defining strength when it comes to resilience.
Okay, that makes sense. Now, all this robustness, all this micro-consensus, state tracking, topology optimization, careful coordination, sounds like it could potentially add a lot of overhead. Is PCCL actually performant enough for real-world ML training, or is all this resilience purchased at too high a computational cost?
That's always the key concern, isn't it? Resilience is great, but not if it makes your training take twice as long. The paper details how PCCL is designed from the ground up to be a remarkably lightweight wrapper around raw socket operations. The error handling and recovery paths are designed to be extremely inexpensive.
Lightweight. How's lightweight?
Well, for instance, they show a benchmark for a small MNIST model just as a basic test. An asynchronous all-reduce call, Peaky all-reduce async, executed over a local loopback connection. So minimal network latency showed a remarkably low latency of just 0.005292 milliseconds.
Wow, that's tiny. 5 microseconds.
Exactly. This demonstrates that the inherent overhead of the PCCL framework itself for its core operations is minimal. This is absolutely critical for maintaining competitive training speeds, especially when the actual computation per step is fast.
That's a critical technical detail. Low latency is non-negotiable for most modern distributed training workloads. It's not just about surviving failures, it's about actually performing well.
And the proof isn't just in those micro benchmarks, they put it through the ringer. The library passes extensive 8-hour-long stress tests as part of their continuous integration CI pipeline, and these run across Linux, macOS, and Windows.
8 hours. What do these tests involve?
They are incredibly aggressive, deliberately trying to break the system in every way possible. They involve high-frequency training loops, simulating iterations happening every 100 milliseconds or so, combined with random peer churn.
So machines just joining and leaving constantly.
Constantly and randomly. New peer processes are being spawned and then abruptly killed every 500 to 1,000 milliseconds throughout the entire 8-hour run. This is designed to induce every possible timing issue, race condition, and failure scenario over a long, sustained period.
Wow, it's brutal.
It is. It's designed to be.
So what does this all mean for you, the developer or researcher, considering using this? This rigorous testing isn't just academic bragging rights. It validates PCCL's ability to correctly unwind all those potential error paths, to safely schedule concurrent operations even amidst chaos, and to reliably maintain that critical shared state despite extreme churn and unpredictability.
It's a testament to the meticulous engineering effort involved to achieve this level of resilience in such dynamic environments. It's not just a theoretical claim, it's been proven under fire, suggesting it's actually ready for the messy reality of the real world.
Okay, it's clear that PCCL is a powerful foundational technology, a really solid base layer. But as you said, it isn't a training algorithm itself. It's more like a general-purpose collective communication library. It provides the low-level primitives, the essential building blocks for implementing various distributed computing algorithms.
Exactly. It's like providing a really robust, fault-tolerant set of power tools rather than a finished piece of furniture. The builders still need to use the tools correctly.
Yeah.
And the developers explicitly state their hope that PCCL will serve precisely as that foundational tool. This means it can enable not just the implementation of pre-existing distributed training algorithms, like distributed data parallel, DDP, but also, critically, facilitate future research in designing entirely new ones. It genuinely opens up new avenues for innovation that were previously just too difficult or impossible because of unreliable communication or the inability to guarantee that crucial bit parity in dynamic settings.
Okay, so let's talk about how you'd use these tools. Even though a straightforward distributed data parallel, or DDP, approach isn't always the best fit for public internet training, mostly because it requires such frequent communication after every single step. Yeah, that can be a bottleneck over high latency links.
It's still an excellent starting point to demonstrate PCCL's programming paradigm and show how it ensures that consistency we've been talking about.
That's right. It's a good pedagogical example. Let's walk through the pseudocode for a typical DDP-like training loop using PCCL. First, at the beginning of each training iteration, you'd likely call update topology. The C here represents the PCCL communicator object. This call checks for and potentially accepts any new peers that might have registered to join the group since the last iteration finished.
Okay, let new people in if they're waiting. Exactly. Then you'd immediately call sync shared state, C shared state. This is the function that ensures all peers currently in the accepted group have a bit identical copy of the model parameters and the optimizer state. And this call is designed to be highly efficient. If everyone's state hash matches the consensus hash held by the master, it's essentially a no-op very fast. The only time it does significant work is if a new peer has just joined and needs to download the current state, or if a peer somehow got out of sync and needs correction.
Makes sense. So check for new members, make sure everyone's on the same page state-wise. Then what?
Then standard DDP stuff. Each peer independently performs its local forward pass on its own mini batch of data, calculates the loss, and then performs a backward pass to compute its local gradients.
Standard local computation.
Right. The crucial collective communication step comes next. All reduce. C. Gradients. ADG. This uses PCCL's all reduce primitive to sum up all the local gradients from all the active peers and then average them. Finally, with the average gradients now available identically on all peers, each peer independently calls optimizer.step to apply these average gradients and update its local copy of the model parameters.
But the critical part here is
The critical part is that because of PCCL's bit parity guarantee on the all reduce output, every peer holds the exact same average of gradients after that step. And since the optimizer step itself, like AtomW, is deterministic, every peer independently calculates and arrives at precisely the same updated model state.
maintaining that perfect bit parity, iteration after iteration.
Exactly, no divergence.
Okay, that clarity on DDP and bit parity is super important. Now, if DDP, with its constant chatter after every step, isn't ideal for public networks, where does DeLoco distributed low communication fit in? The name itself suggests it's tackling that communication overhead challenge head-on.
DeLoco is indeed a brilliant solution, engineered specifically for those high-latency, lower bandwidth public network environments where DDP would struggle. It takes inspiration from ideas in federated averaging, and it elegantly divides the training loop into two distinct phases.
Phases.
Yeah. There's an interphase. During this phase, each peer trains completely locally for a set number of steps, let's call it H steps, using a standard optimizer like AtomW on its own data. Crucially, during these H intersteps, there is absolutely no communication whatsoever between the peers. They just compute locally.
So you do multiple local steps before talking.
Exactly. This dramatically reduces the overall communication frequency, making it far more practical and efficient over the public internet compared to DDP's constant communication.
Okay, that's the interface. What happens after H steps?
After these H local steps are completed, we transition to the outer phase. Here's where the synchronization happens. Each peer computes its parameter difference, or delta. This delta is calculated by comparing its current local model parameters, let's call them, with a global aggregator parameter set, which represents the consensus state from the previous outer iteration.
So how much did my local model change from the last global state?
Precisely. These differences, these deltas from all the peers, are then collectively merged, typically averaged, using an all-reduce operation provided by PCCL, just like in DDP, but applied to the deltas instead of gradients. This average delta effectively forms a kind of outer gradient. This outer gradient is then applied by a separate outer optimizer. The paper suggests using something like Nesterov momentum to update the global aggregator parameters. This updated do then becomes the starting point for the next interphase on all peers.
Interesting. So you have local steps, calculate the change, average the changes, and apply that average change globally.
That's the core idea.
So what does this all mean for someone actually trying to train across these unreliable, geographically dispersed networks?
It means you have a knob to turn. The fact that synchronization only occurs once per H steps rather than every single mini batch makes DeLoco vastly more suitable for public internet training. You're not constantly overwhelming the network. You can tune H, the number of local steps, to find that sweet spot, balancing faster local computation against less frequent but still necessary global synchronization.
More local steps means less communication, but maybe slower convergence.
Potentially, yes. It's a trade-off. Finding the right H depends on the model, the data, and the network characteristics. But it gives you control. And the paper also notes a fascinating connection. DeLoco, when you set H1, meaning only one local step per outer iteration, and use a simple outer SGD optimizer with a learning rate of 1.0, becomes roughly equivalent to standard DDP, assuming the inner optimizer states are comparable.
So DDP is just a special case of DeLoco.
In a sense, yes. It shows that DeLoco isn't some completely alien paradigm, but rather exists on a continuum. It allows you to configure your training anywhere from frequent DDP-like communication, H1, to much more infrequent communication, large H, letting you trade off convergence behavior for significantly reduced network load.
That's really flexible. Now, DeLoco sounds pretty good for reducing communication. But then there's async DeLoco. This sounds like it takes it even a step further by trying to overlap the global reduce phase with the local compute, trying to hide that communication latency entirely. That's always the holy grail in distributed systems.
It is indeed the holy grail. And async DeLoco uses a clever trick to get closer to it. The key idea is a one-step delay in applying the global update.
One-step delay, how does that work?
Instead of performing the H-local steps, then calculating the delta, then doing the all-reduce, and then waiting for that all-reduce to finish before applying the update and starting the next H steps.
Which involves network waiting time.
Right, potentially significant waiting time. Instead, in async to loco, after finishing the H-local steps and calculating the delta, the peer immediately kicks off the all-reduce operation asynchronously in the background using PCCL's async capabilities. And crucially, it doesn't wait. It immediately proceeds to start the next round of H-local training steps using the current global parameters H.
So it's computing while the previous communication is happening.
Exactly. Meanwhile, that previous iteration's all-reduce of the deltas completes asynchronously in the background. The result of that background all-reduce, the average delta, is then applied by the outer optimizer to update at the beginning of the following outer iteration, just before the next set of local steps begin.
So the update you apply is always based on the computation from the previous round of H steps.
Precisely. You're always working with global parameters that are effectively one outer step behind the very latest local computations. But the critical benefit is that the communication overhead, the time spent waiting for that all-reduce, is effectively hidden behind the local computation of the next H steps. This means potentially much less idle time waiting for the network.
This is a really important implication. Communication overhead gets masked by useful computation. It's a trade-off. Clearly, you're applying parameters that are slightly stale, one step behind, but the potential gain in overall wall clock time could be huge, especially on slow networks. Wall clock time is often the metric that matters most for these massive training runs.
Absolutely. Faster time to solution, even if the convergence path is slightly different. And this is where PCCL's sophisticated fault tolerance really shines, because handling peer churn in this complex asynchronous one-step delayed model is incredibly tricky. But PCCL's architecture provides the necessary primitives to make it robust and maintain consistency.
How does it manage churn in that async pipeline?
Okay, there are several key aspects. Firstly, PCCL strictly enforces that rule of no overlap of major operations. Remember, only one major operation, topology update, state sync, or a collective like all-reduce, can be active at a time per group. So if a peer fails right in the middle of that background, asynchronous all-reduce, PCCL detects it, aborts that specific all-reduce attempt, reconfigures the group membership by marking the peer as gone, and then allows the next collective, perhaps the retry of the failed one or the one for the subsequent outer step, to begin with the updated group. This strict sequencing prevents any internal inconsistencies or race conditions that could easily arise from overlapping state changes in an async model.
Okay, clean abort and retry with a new group. What about new peers joining? How do they catch up with this one-step behind state?
That's a really nuanced challenge, reconciling the one-step behind updates for newcomers. A new peer arriving mid-run in an async to loco setup is in a unique situation. It can't just grab the current start computing. First, it must synchronize shared state to get the most recent outer parameters and the outer optimizer state from the active group. Then, it needs to reset its inner model by copying those aggregator parameters to its local parameters. Okay, now it has the same starting point. But here's the tricky part. It needs to enter the one-step behind pipeline correctly. It missed the completion of the previous background. All-reduce, the one whose result determined the G that it just received.
It doesn't know the delta that was just applied.
Exactly. So an additional targeted shared state synchronization is required. This effectively allows the newcomer to eavesdrop on the result, the average delta, of the all-reduce it missed. PCCL facilitates this. This ensures that even late joiners can correctly initialize their state and maintain bit parity with the rest of the group within the async logic.
Wow, that's intricate. How does the system manage pausing for these updates?
It manages these membership changes gracefully by temporarily stalling the pipeline when necessary. There's a check, CA peer spending, which efficiently queries the master without adding I/O overhead because it uses a separate TCP control stream to see if any peers are registered and waiting to be voted in. If this returns true, the system knows a membership change might be imminent. It first checks for and awaits the completion of any currently in-flight asynchronous collectives. Can't change membership while communication is happening. Only after any ongoing collectives finish can it safely call c.update topology to potentially accept the new peers, followed by C-sync shared state, to bring them fully up to date, including that special eavesdropping sync if needed for async to loco. This careful sequence ensures that the global state is consistent and stable before the new peer fully joins the active training loop.
Makes sense. Got to drain the pipes before changing the plumbing.
Good analogy. And finally, there's the aspect of ensuring global consistency once a new peer is accepted, especially during that initial state synchronization. The new peer needs to adopt the outer state and optimizer state from the existing trusted peers. The paper specifically mentions using different strategies here, like send only from the existing peers or receive only by the new peer, rather than the default enforce popular strategy, which might involve voting on the correct state. Why? To avoid undesirable state propagation if, for example, a whole bunch of new peers join simultaneously, potentially without the correct state yet.
Ah, you want the established peer state to be the source of truth.
Exactly. The pre-existing peers, which hold the latest valid global state, actively provide that state to the newcomers, preventing a scenario where the state might get corrupted or reset to something incorrect if the newcomers accidentally outvote the correct state during the sync.
Got it. Prioritize the known good state. So let's tie this together. What does this all mean for you, the person actually trying to do large-scale training?
It means this robust capability to allow peer churn handling nodes joining and leaving while sustaining this complex one-step behind global update mechanism enables truly scalable and resilient training, even in unreliable or heterogeneous environments like the public internet or using spot instances. You get the benefits of DeLoco's reduced communication frequency, the potential performance gains of async DeLoco's overlap, and the resilience to keep training even when your infrastructure is dynamic. You can strategically tune DeLoco's InterStux H to balance local compute with global communication needs, potentially hiding all that expensive communication overhead behind local computations. It makes training on public networks not just possible, but genuinely performant and cost-effective.
It sounds like a powerful toolkit for making distributed, resilient ML a practical reality. That's a phenomenal overview of how PCCL enables these advanced training algorithms like async DeLoco. But now, let's pull back the curtain even further and really get into the weeds. Let's look at the nuts and bolts. How does PCCL actually perform its core collective operation, the all-reduce, at such a low level? Especially while making all these guarantees about bit parity and fault tolerance.
Right, let's dive into the engine room. PCCL utilizes a highly optimized implementation of a classic algorithm called N1 pipeline ring reduce. Here, N is the world size, the total number of active peers participating in the operation.
Pipeline ring reduce, okay. How does that work?
To visualize it, imagine the large tensor you want to reduce, like the gradients or the DeLoco deltas being broken down into n equally sized slices or chunks. The process that unfolds in several distinct phases. First, obviously, is partitioning the tensor and defining these chunk boundaries. Then comes the core reduce scatter phase. In this phase, each rank or peer operates in a logical ring. It progressively sends one chunk of its local data to its neighbor in one direction around the ring, while simultaneously receiving a chunk from its neighbor in the other direction. As the incoming data, representing partial sums from upstream, arrives, it's immediately accumulated into the peer's local buffer using the specified reduce op, like SUM. The send-receive-accumulated step repeats n1 times. After exactly n1 steps, each rank will have received contributions from all other ranks for one specific chunk of the original tensor. So each rank now owns one fully reduced chunk.
Ah, so the reduction happens piece by piece as data moves around the ring.
Exactly. It's pipelined for efficiency. Following the reduce scatter is the all gather phase. The paper might call it reduce gather, but it functions like an all gather. Here, each rank, now holding its fully reduced chunk, needs to share it with everyone else so they all have the complete result. So each rank broadcasts its completed chunk around the ring. Again, this typically takes n1 steps, with peers sending the chunk they just received in the previous step. By the end, all peers have received all n fully reduced chunks, reconstructing the entire result tensor.
Okay, reduce scatter to get reduced chunks, then all gather to share them.
Precisely. And finally, there might be a finalized step. If the requested operation was, say, average, AVG, this is where the final division by n, the world size, is applied to the buffer on each peer. Now, crucially, throughout all these send-receive-accumulate steps, PCCL is constantly checking for potential issues. If an I/O failure occurs, maybe a connection drops, a socket errors out, the entire operation is immediately aborted.
How does it abort cleanly?
The implementation ensures that the buffer holding the tensor data is restored to its exact pre-operation state. No partial results are left behind, preventing any data corruption or inconsistency. And these abort checks are performed periodically by polling the master socket asynchronously. This incurs no additional I/O overhead on the data path itself because it uses that separate, dedicated TCP stream just for control messages with the master.
That zero copy, often operating directly on GPU buffers, pipeline nature, combined with that robust abort and restore recovery mechanism,
Yeah.
that seems absolutely fundamental to both its impressive performance and its fault tolerance. It's an elegant dance between speed and safety.
It really is. It's designed to handle failure as a first-class citizen, not an afterthought.
Okay, building something this robust, this low level, across diverse operating systems, different GPU architectures, and unpredictable network conditions that must come with its own unique set of immense technical hurdles. What were some of the biggest technical headaches the developers likely faced? The kind of really gnarly, frustrating details that don't often make it into the polished, final research paper.
Oh, you can bet there were plenty of those. The paper actually hints at several, which is quite refreshing. One major category of issues was the sheer variance in socket implementation behavior across different operating systems.
Sockets are tricky beasts.
They really are, especially at the edges. TCP/IP socket APIs differ quite drastically, for example, between Windows sockets, WSA, and the more traditional BSD-style implementations you find on Linux and macOS. This isn't just about function names, it's about subtle behaviors. They mention needing extensive CI testing and aggressive stress testing just to validate behavior and work around various quirks they observed. Things like different blocking or unblocking behaviors for the rec-C, call when the other side calls close or shut down. Subtle differences in how half-closed connections drain data on Windows. They even mention suspecting potential bugs in Apple's XNU kernel related to send buffer exhaustion under specific load conditions.
Wow, so they're debugging potential OS kernel issues.
It sounds like it. Managing these low-level OS-specific differences is notoriously difficult, especially because they often only manifest under heavy load or very specific timing conditions, making them incredibly hard to reproduce and debug.
Nightmare fuel for systems programmers.
Absolutely. Another significant challenge they tackled was named Thread Park. To really saturate full duplex network links, sending and receiving simultaneously at full speed and maximize throughput for collective operations, PCCL utilizes dedicated send threads and dedicated receive threads for each peer-to-peer connection.
Lots of threads.
Potentially hundreds or even thousands in a large job. Now, you need a way for these threads to efficiently wait for work, like data arriving or buffer space becoming available, and be woken up instantly when needed. Standard C++ condition variables, while generally robust, apparently proved too slow, too much overhead for the ultra-low latency wake-up system PCCL requires.
So they built their own synchronization primitive.
Essentially, yes. They developed a custom low-latency wake-up library they call ThreadPark. It uses platform-specific Futex-like APIs across all major operating systems. This means using Linux's raw Futex system call, match Auceris undocumented ulock-wait primitive, and Windows's wait and address wake-by-address single functions.
Oh, those are deep kernel-level synchronization primitives, way beyond standard mutexes.
Exactly. They allow threads to efficiently park themselves without consuming CPU cycles and be woken up directly by another thread, modifying a specific memory address, minimizing kernel transitions, and scheduler overhead. It's about squeezing out every last microsecond of latency.
This raises an important question, though. Relying on such deep, sometimes undocumented kernel-level OS-specific optimizations like ThreadPark and navigating those subtle socket behaviors, does this create a substantial long-term maintenance burden? Or perhaps limit future platform portability if these underlying OS APIs change significantly in future versions? It's clearly a massive engineering feat, but what are the potential downstream implications of digging that deep?
That's a very astute point and a classic trade-off in high-performance systems programming. You're absolutely right. While these deep optimizations deliver the necessary performance and stability for PCCL's goals, they absolutely increase the complexity of maintenance and the risk associated with future portability. Any significant OS update could potentially introduce subtle changes to these low-level APIs or behaviors, requiring the PCCL developers to investigate, adapt, and revalidate. It's a constant vigilance task. However, the authors likely weighed this against the sheer necessity of achieving their core objectives, robust fault tolerance and high performance over the public internet, which they probably concluded simply weren't possible using only higher-level, more portable abstractions. Those abstractions often hide the very details you need to control for this kind of resilience.
So the ends justified the means, essentially.
It seems so. The level of detail discussed here is indeed rare in most research papers, precisely because it speaks volumes about the depth of engineering required to solve this specific hard problem effectively, not just theoretically.
Okay, what else? Any other major hurdles?
Another massive undertaking they mention was achieving what they term zero copy, bitwise deterministic, interruptible, pipelined, quantized, asynchronous, and concurrent collective communications.
Wow, that's quite a mouthful. Let's unpack that.
Yeah, it covers a lot. Zero copy means PCCL tries to directly reference user-provided buffers like the memory holding a PyTorch tensor on the GPU for its network send operations, avoiding costly memory copies between CPU and GPU or within memory. Big performance win. Bitwise deterministic, we've covered ensuring identical results everywhere. Interruptible refers to that ability to abort operations cleanly on failure. Pipelined is the ring-reduce algorithm itself. Quantized means it needs to work correctly even when using lower precision numbers during training, which introduces its own determinism challenges. Asynchronous is needed for things like async to loco, and concurrent refers to handling multiple operations potentially happening across the system, though only one may do one per group. Making all of these things work together reliably, especially the interruptibility ensuring correct unwinding from I/O failures mid-pipeline, discarding any partially sent data, and enabling concurrent polling of the master for state changes without degrading performance required incredibly careful design. They even mention needing a custom caching allocator to achieve zero malloc paths for the core reduced code, avoiding any dynamic memory allocation overhead during those critical high-performance operations.
Zero malloc. That's serious optimization.
It is. Then, specifically for bitwise determinism with quantization. While a standard pipelined ring reduce using full precision floats can be deterministic, using quantized formats like FP8 or INT8 adds complexity because the dequantization followed by quantization isn't perfectly reversible. DQX doesn't always equal X due to precision loss. PCCL had to make specific implementation choices to ensure determinism even with quantization. This likely involves ensuring all peers perform quantization and dequantization steps at precisely the same points in the algorithm and avoiding reliance on any lingering higher precision intermediate values that might not be available or identical across all peers, especially if they have slightly different hardware. Everyone has to play by the exact same low precision rules.
Fascinating. And you mentioned hardware differences.
Yeah.
What about the GPUs themselves?
Yes. A truly deep dive was needed into the determinism of NVIDIA PTX intrinsics. To absolutely guarantee bit-identical advancement of the shared state, the numerical behavior of computations performed on the GPUs themselves must be identical across all participating hardware.
Even across different generations of GPUs.
Ideally, yes, or at least within the range you expect to support. While GPUs are massively parallel, the underlying principle holds. If all threads execute the exact same code deterministically, the results can be consistent. The challenge is that NVIDIA's PTX code, their low-level instruction set, only has soft-forward compatibility. While newer GPUs can often run code compiled for older ones, there's no absolute guarantee from NVIDIA that the numerical results of all instructions or, more subtly, the lib-device mathematical intrinsics will be bit-for-bit identical across all hardware generations.
Oh, wow. So even fundamental math operations might differ slightly.
It's a theoretical possibility they had to address. The paper specifically mentions they validated the behavior of NVEX-PICOF, a PTX intrinsic for calculating the exponential function across a very wide range of NVIDIA architectures. They tested everything from an old Maxwell GPU, GTX 980 Ti, up to the then latest Hopper-Blackwell, B200.
How do they validate it?
By hashing the output of NVEX-PIC for all possible 232 single precision float bit patterns on each architecture, and confirming that the resulting hash was identical across all of them.
They tested 4 billion input values on every GPU architecture.
It sounds like it. That's the level of rigor needed to be absolutely sure that this fundamental building block would behave identically everywhere, ensuring that subtle hardware differences wouldn't break their bit parity guarantee.
So just to be absolutely crystal clear here,
Sure.
if even one GPU model in a cluster of 1,000 had a slightly different non-bit identical way of calculating something as fundamental as XBEF at the hardware or intrinsic level, that could potentially, over time, completely break PCCL's core promise of bit parity for the entire model state.
That's the risk they needed to mitigate, yes.
This is an incredible deep dive into the absolute lowest levels of computation. It implies an extreme, almost obsessive attention to detail just to ensure consistency across potentially heterogeneous hardware. That's a problem the paper doesn't explicitly frame as a major challenge they set out to solve, but they clearly invested a massive amount of effort into verifying and ensuring it wouldn't bite them. It's like discovering a single pixel might be out of place on a massive, high-resolution digital canvas and realizing that single pixel could potentially ruin the entire painting if not accounted for. Astounding level of detail. Okay, with all that incredible deep engineering under the hood, ensuring determinism down to the GPU intrinsic level, how does PCCL actually perform? Let's start with the traditional scenario.
Hmm.
How does it stack up against existing, highly optimized libraries in a standard high-performance computing setting? You know, on a fast, reliable, local cluster, the kind of environment where libraries like Glue are specifically designed to shine?
Right, the home turf for traditional libraries. Even though PCCL's primary design goal isn't just raw speed on these pristine, reliable clusters, its focus is really on fault tolerance and resilience over WAN. It still remains remarkably competitive with Glue. Glue is PyTorch's default collective library, specifically optimized for these kinds of on-premise, tightly coupled clusters. In terms of raw, reduced throughput, the benchmarks show PCCL generally holds its own against Glue. It's worth noting, though, that PCCL's core design for abortability, the ability to safely stop and restart collectives, does put it at a slight theoretical disadvantage in these pure speed tests.
So.
Because ensuring abortability requires those extra checks and coordination points, likely involving more VTEX syscalls, those low-level thread parking calls we discussed, during the collective operations compared to a library like Glue that assumes failures won't happen mid-operation. This makes PCCL potentially a bit more sensitive to OS scheduler-induced latencies and can result in slightly higher variance in its throughput measurements on these ideal networks. But the fact that it's still competitive, often matching or nearing Glue's throughput, despite carrying this necessary architectural overhead for fault tolerance, is actually very impressive.
That's a really important implication, isn't it? PCCL isn't just about being fault-tolerant. It's also designed to be genuinely performant, even on high-speed networks where you might not need the fault tolerance as much. It counters that common misconception that robustness always has to come at a significant, unavoidable cost to raw speed. It's a subtle technical detail, but one that underscores the quality of the engineering.
Exactly. They didn't sacrifice performance entirely for robustness. They aimed for both.
But, okay, the real magic, the place PCCL was truly designed for, happens when we talk about performance over the public internet, over wide area networks, WANs. And this involved one of PCCL's key insights you touched on earlier, the surprising power of using multiple connections over the WAN. Why does it matter how many parallel PCP connections you open between nodes when you're communicating over the internet? Feels counterintuitive initially.
It does seem counterintuitive, but it's a profound observation for practical WAN communication performance. On the public internet, simply opening and utilizing multiple simultaneous TCP connections between the same two peers can dramatically boost the total achievable bandwidth you get between them.
Why? What's going on there?
There are a couple of primary reasons for this effect. First, standard TCP includes mechanisms for congestion control and receive window auto-scaling. Especially on these high-latency, high-bandwidth WAN links, sometimes called long-fat networks or LFNs, these mechanisms often struggle to fully saturate the pipe. The feedback loop is too slow, and a single TCP connection might conservatively underutilize the actual available bandwidth. Surprisingly, sometimes even disabling auto-scaling can make performance worse. It's tricky.
So one connection might be too cautious.
It often is. Second, and often even more impactful, is how many internet routers handle traffic. Many routers employ some form of per-flow fair queuing. This means if you have multiple distinct data flows, and each TCP connection is typically treated as a separate flow going through the router will try to give each flow a fair share of the available outgoing bandwidth.
So if I only have one flow, I get one share. If I have 10 flows.
You might get 10 smaller shares, but the sum of those 10 shares could be significantly larger than the single share you got before, especially if other traffic is also competing for bandwidth. By running several parallel TCP streams between peers, PCCL can effectively carve out extra bandwidth slices that a single flow alone might not receive under these fair queuing policies. This means that when PCCL needs to perform multiple collective operations, or even break down a single large one, it can dispatch these operations concurrently across multiple connections drawn from its internal peer-to-peer connection pool. The result is significantly higher aggregate bandwidth utilization between the nodes.
Wow. Okay, so multiple connections aren't just a redundancy. They're actively exploiting network behavior to get more throughput.
Exactly. It's a performance hack rooted in understanding real-world internet infrastructure.
And the paper shows this effect is really pronounced, right? Especially for those challenging cross-continental connections, like the example they gave from Nebius in Helsinki, Finland, all the way to Voltage Park in Dallas, Texas.
Absolutely.
This is a technical detail that dramatically changes the landscape of how you'd approach WAN communication for machine learning. It enables efficient communication patterns that were previously just unthinkable without leasing expensive, dedicated, private network lines.
To truly drive this point home, the paper presents results from several WAN all-reduce benchmarks run across real-world, geographically dispersed cloud compute nodes. Let's look at Experiment 1, all-reduce across North America and Europe. Here, they performed an all-reduce operation on a 1.073 gigabit tensor across 18 nodes. These nodes were spread across locations like Oregon and Texas in the US and Germany and the UK in Europe. A truly global setup.
Okay, what was the baseline performance?
As you'd expect, this setup was significantly bottlenecked by the high latency of the undersea cables and the vast geographical distances. Using a single connection approach, it achieved an effective throughput of just 11.85 megahertz. The bandwidth utilization per peer was around 358.4 megabits. Slow.
Yeah, 1 GB taking around 90 seconds for one reduce. That vividly highlights the inherent challenges of cross-continental training without specific optimizations like PCCLs. It's painfully slow if you do it frequently.
Painfully slow. But that's precisely where Experiment 1.1, Concurrent Connections North America plus Europe, demonstrates the power of PCCL's multi-connection strategy. By utilizing 128 concurrent connections, managed by PCCL's internal connection pool, to handle multiple concurrent all-reduce operations, or perhaps pipeline chunks of a single large one.
The total time.
The total time for the equivalent operation dramatically reduced from that 90.5 seconds with a single connection baseline down to just 10.726 seconds.
Wow, almost a 9x speed up.
Exactly. And this resulted in an aggregate bandwidth utilization across the entire system peaking at 24.54 gigabits, a massive improvement.
That is a staggering performance gain, achieved simply by intelligently dispatching the work over multiple parallel connections. It's a crucial technical aspect for making WAN training practical. And if you look at the map provided in the source materials, Image 1, you can really visualize these connections spanning across North America and deep into Europe, highlighting the sheer geographical dispersion and the formidable communication challenge they're overcoming with this technique.
Now, let's move to a slightly less geographically dispersed setup. Experiment 2. All reduce across North America. This involved all reducing the same 1.073 gigabit tensor, but this time across 12 nodes located within North America, places like Oregon, Texas, and Quebec.
Closer proximity, so baseline should be better.
Right, and it was. This setup naturally achieved a faster effective throughput of 30.48 megabits and a bandwidth utilization of around 897.6 megabits per peer using the single connection baseline. Better than transatlantic, but still not super fast for a gigabyte.
And looking at the map for this experiment, Image 2 in the source materials, you can visually appreciate how PCCL's topology optimization, that HESP solver finding the best ring order, would likely play a significant role here too, finding the most efficient communication paths between these geographically spread nodes within the continent to minimize latency even before considering multiple connections.
Absolutely. Topology optimization and multiple connections work hand in hand. And sure enough, in Experiment 2.1, Concurrent Connections North America, when they again used 128 concurrent connections, the time for the all-reduce dropped further to just 9.419 seconds. The aggregate bandwidth utilization climbed to an impressive 27.57 Gbps. Consistent, significant improvement.
Okay, one more region.
Finally, they looked at a more tightly coupled regional experiment, Experiment 3, All Reduce Europe West. This used the same 1.073 gigabit tensor, but across just 6 nodes located relatively close together in Western Europe, Frankfurt, Paris, London, etc. Here, the much closer proximity and lower latency allowed for significantly faster baseline results, even with a single connection. They achieved 129.2 millibits effective throughput and a bandwidth utilization of 3.67 gigabits per peer. Much faster already.
And the map for this one, Image 3 in the source materials, vividly illustrates that relatively tighter cluster of nodes in Western Europe, which inherently explains the much higher baseline performance compared to the cross-continental or even cross-North America setups.
Exactly. But even here, there was room for improvement. In Experiment 3.1, Concurrent Connections Europe West, unleashing those 128 concurrent connections further reduced the all-reduced time to a remarkably quick 5.066 seconds. And the aggregate bandwidth utilization shot up to a massive 45.74 gigabits.
Wow. So the pattern is crystal clear. Concurrent connections are a critical performance lever for WAN communication in distributed ML, and PCCL is built to exploit this.
Absolutely. It's not just a minor tweak. It's a fundamental performance accelerator for these scenarios.
So after seeing all these impressive PCCL benchmarks, how did it compare directly against a widely used alternative like glue, especially in these challenging WAN conditions? Do they run glue over the internet too?
Yes, the paper directly compares PCCL to glue in these WAN settings. They were able to run glue without needing a VPN in these specific experiments because the cloud nodes they used happened to have internal IP addresses that were routable within the provider's network, allowing for a more direct apples-to-apples comparison of the libraries themselves.
Okay, and the results.
Across all the WAN experiments, glue consistently showed a performance gap compared to PCCL. PCCL offered improvements in the actual reduced time, ranging from about 4.15% for the most challenging North America plus Europe setup, up to a more significant 14.17% improvement for the relatively faster Europe West experiment.
So PCCL was faster in all WAN cases. Why?
The paper attributes this performance difference primarily to two factors. First, Glue lacks the sophisticated dynamic topology optimization that PCCL performs using its APSP solver. Glue likely just used a default or arbitrary ring order, which is often suboptimal over ones with varying internode latencies. PCCL finds a better path. But perhaps even more crucially, Glue doesn't natively support dispatching work across concurrent all-reduce operations in the way PCCL does. It wasn't designed with that multi-connection WAN trick in mind. So Glue simply misses out on that biggest lever for maximizing WAN throughput that PCCL leverages so effectively.
This comparison really highlights the difference, doesn't it? PCCL's tailored design, built from the ground up for the specific challenges and opportunities of the public internet, versus libraries like Glue that were primarily built for more controlled, high-performance, local cluster environments. It's a specialized tool solving a specialized and increasingly critical problem.
Exactly. Different tools for different jobs, and PCCL is the right tool for this particular job.
Okay, so we've dissected PCCL's architecture, its intricate fault tolerance mechanisms, its clever performance optimizations like topology awareness and concurrent connections. Now let's zoom out a bit. How does PCCL fit into the broader existing landscape of distributed training tools and libraries? What makes it truly stand apart from other solutions that people might have heard of or used? And what was the specific gap in the ecosystem that it aimed to fill?
That's a great question for context. PCCL really carves out a very specific and I think incredibly important niche by uniquely prioritizing both robust, low-level fault tolerance and guaranteed bit parity, specifically within dynamic, potentially unreliable environments like the public internet. Let's look at some related work mentioned in the paper to highlight this distinction. First, there's Glue, which we just discussed in the benchmarks. As we said, Glue is highly optimized for on-premise co-located clusters. It fundamentally assumes full peer reachability over a secure local network. It's just not designed for the public internet out of the box and typically requires setting up a VPN, which adds its own layer of overhead, complexity, and potential performance bottlenecks. The paper mentions previous work, like a project called Intellect One that tried to use Glue for large-scale WAN training, but it required significant manual intervention and custom scripting just to deal with connection issues and peer failures. PCCL aims to completely eliminate that need for manual handholding with its automatic, robust join recovery and state synchronization procedures.
So PCCL addresses a fundamental limitation of Glue for WAN scenarios. What about other approaches?
Then there's a framework called HiveMind. HiveMind takes a very different approach. It's decentralized, relying on gossip-based protocols for communication. It often uses gradient compressors to reduce bandwidth requirements and operates using best effort RPCs and simple timeouts to handle peer churn.
Decentralized sounds good for resilience.
It offers a certain kind of resilience and flexibility, absolutely. HiveMind allows workers to join and leave quite freely without needing global coordination. However, the trade-off is that it completely sacrifices strict synchronization. Collective results in HiveMind only converge eventually towards an average state, not bid exactly in each step. This means deterministic state progression, especially across heterogeneous hardware, is simply unattainable with HiveMind's model.
So HiveMind prioritizes flexibility and relaxed consistency.
Exactly. Whereas PCCL, in stark contrast, makes that strict bit parity guarantee its absolute foundational promise. Different philosophies for different needs.
Okay, any others?
And finally, the paper contrasts PCCL with Horovod plus Elastic. Horovod is another popular framework that often uses MPI or Glue for its collectives. The Elastic extension adds Python-level mechanisms for handling dynamic worker membership, using things like rendezvous points and an in-memory rollback API. However, recovery from failures in Horovod Elastic typically involves explicit rollbacks to previous checkpoints, which the paper notes can incur significant latency, potentially seconds interrupting the training flow. It also relies heavily on application-level checkpoint hooks and user-implemented logic for saving and restoring state. The user has to manage the recovery details.
And the consistency.
Crucially, Horovod Elastic also doesn't inherently guarantee bit-identical state across all the ranks after a recovery. It aims for logical equivalence, relying on the user to supply state objects that can be correctly restored. But it doesn't enforce that strict bit-for-bit match that PCCL does through its low-level microconsensus and shared state hashing. PCCL's fault tolerance is built in at a lower level, uses those fast microconsensus steps, and enforces bit-exact state with error recovery paths designed to be just as fast as the success paths.
What's truly fascinating here, listening to these comparisons, is how PCCL really did carve out its own unique niche. It seems it was laser-focused on providing that combination of low-level transparent fault tolerance with absolute guaranteed bit-exact state consistency. That specific combination seems to be a gap that the other solutions didn't fully address, either compromising on the strict consistency or handling failures at a higher, potentially slower application level.
I think that's a perfect summary. It's not just about getting to a good enough or eventually consistent state. It's about maintaining that precise, bit-for-bit identical state across all nodes, no matter what chaos the network or infrastructure throws at it. That precise guarantee is a huge distinction and enables a level of trust and reproducibility that was hard to achieve before in these dynamic settings.
Okay, so let's bring this home. What does this all mean for you, for someone listening who might be looking to actually use this technology in the real world? What are the tangible benefits and practical implications that translate directly to real-world impact for machine learning development and deployment?
The practical implications are quite significant, really potentially changing the game for how large-scale distributed ML is done. Firstly, and this is a big one economically, PCCL makes training on spot instances practically feasible and incredibly stable.
Those cheap but interruptible cloud instances.
Exactly. They can offer massive cost savings, sometimes 70–90% cheaper than on-demand instances, but they come with the risk of being terminated by the cloud provider with very little notice. With PCCL, as long as you architect your setup to have at least one persistent non-spot instance acting as your master node, and perhaps holding a reliable checkpoint.
The master needs to be stable.
Right, the master should be stable. Then the training run itself is guaranteed to remain stable, even if many or most of the spot worker instances get terminated and replaced. Loss of the overall training state becomes essentially impossible due to PCCL's robust state management and recovery. This dramatically reduces the financial barrier to entry for training truly enormous models, making it accessible to a much broader range of projects, researchers, and companies.
That's huge for democratization. What else?
Secondly, it allows for the aggregation of compute resources across the internet with previously infeasible ease and reliability. Think about underutilized GPUs sitting in different data centers, maybe in different organizations, or even different continents. PCCL provides the robust communication fabric needed to potentially pool these disparate resources together for a single large training job, reducing wasted compute power globally.
Breaking down silos.
In a way, yes. Thirdly, related to that, it enables seamless hybrid and multi-cloud training. You could orchestrate a single training run across resources spanning different cloud providers, say, using some GPUs on AWS, some on Azure, maybe some on Google Cloud, or even potentially integrate specialized edge devices for certain parts of less communication-intensive workloads. This offers incredible flexibility for optimizing cost, leveraging specialized hardware, and crucially avoiding vendor lock-in.
Gives you options.
Lots of options. And finally, a perhaps subtle but important benefit. PCCL's robust shared state system implicitly provides model protection because resumption after failure, or when a new peer joins, is only allowed from a validated shared state hash that matches the consensus.
The one everyone agrees on.
Right, and peers are expected to be able to restore to that state, perhaps from local checkpoints if they were offline. This categorically rules out those insidious training dynamics inconsistencies that can sometimes be introduced by naive restarts or joining with slightly incorrect state. It ensures that the model always progresses from a known, globally consistent, bit-identical state, enhancing trust and reproducibility.
This really does sound like a game changer, particularly for the economics and the sheer accessibility of large-scale AI training. It seems to democratize access to the massive compute power needed for cutting-edge AI by making inherently unreliable, geographically distributed resources dependable and usable. It transforms the daunting problem of scaling AI training into something that feels much more like a manageable, cost-effective, and robust engineering endeavor.
I think that captures it perfectly. It tackles a fundamental bottleneck and opens up possibilities that were just too difficult or risky before. Hashtag tag tag outro.
Well, today we've taken a really deep dive into PCCL, the Prime Collective Communications Library. It's truly a groundbreaking piece of engineering that tackles the incredibly complex world of distributed machine learning, specifically across the unpredictable, often messy, public internet. From its clever master-client architecture and the concept of microconsensus, to its unique fault tolerance mechanisms that handle peer churn gracefully, and its support for advanced asynchronous training algorithms like async deloco that hide network latency. PCCL is genuinely enabling a new era of resilient, large-scale AI development.
Yeah, it feels like a significant step forward. It's not just making distributed training possible over the internet, which others have tried with varying success. It's making it reliable, efficient, and critically bit identical, which opens doors for innovation that were previously just too expensive, too fragile, or too complex to attempt.
Right. Reliable and cost-effective are the key words there.
And if we connect this to the bigger picture, thinking beyond just the immediate problem solved, PCCL doesn't just address a critical engineering bottleneck, it also opens up a truly fascinating area for future research and exploration. Consider this as a provocative thought. What entirely new optimization strategies, what new distributed algorithms, perhaps even new federated learning paradigms, become possible now that you can reliably and deterministically orchestrate training across truly heterogeneous, dynamic, and globally distributed compute resources? How might this fundamental shift in communication reliability change the very topology of AI development and collaboration itself? Could it foster a more distributed, more robust, perhaps even more globally inclusive research and development ecosystem for AI? The downstream implications could be quite far-reaching.
That's a fantastic point to ponder. What new structures emerge when the communication foundation is this solid, even across chaos? Well, that's it for this deep dive. If you found this discussion on PCCL's intricate technical details and its profound implications as fascinating as we did, and you want to stay updated on the latest AI and ML research papers and breakthroughs, be sure to visit our webpage, neuralintal.org, that's neuralintal.o-rg, and check us out on YouTube as well. Until next time, keep learning, keep building, and keep pushing the boundaries of what's possible in AI.